start now. Think. One more minute. I hope. Huh? Okay. So what I had last was, let me remind you, I started from Lagrangian. What was it? Okay. Then I define spin of the system as this lambda trace sigma I over 2 G, or well, let me write G inverse G dot. I think I used it last time. G sigma 3 G inverse. Okay. Then we found that for this Lagrangian there are, well, then we took a slight detour by writing the momenta so conjugate to the variable psi here to define this object. So this is a function of psi. This always exists, okay. And we found that this Ti with S was, the Poisson bracket was I sigma I over 2S. We found this. This is an important equation. Then we also found primary constraints. Oh, I should write G. Depending on the paper, we change the notation. So, right. So these are old papers, but the different notations we used keeps coming back. I am missing Madhusudan. He comes, is it? Normally he comes. Raman, Madhusudan, no? The student from Bangalore. He was in my office. Okay. So we have this. Then we found primary constraints, Pi, which was Ti minus Si. Then get the Poisson bracket was epsilon ijk pk, but then something strange happened because it had an additional term sk. Okay. Then we found that the first class constraint was of the form, I think we called it Vi Pi, and Vi is parallel to the spin, right? So Vi is some constant times, okay, parallel to spin. These are classical, so it makes sense to talk about Si. And furthermore, what this V dot P did to S, Poisson bracket, is something very natural, which was I S sigma 3 over 2. So it's a gauge transformation. Because remember that this had a gauge invariance, this is Lagrangian, for action on the right, okay, and this is actually, and the Hamiltonian was in fact equal to of this kind, Vi Pi. So Hamiltonian was a first class constraint. Okay. Yeah. S is not there can imagine every time I write S that it is a G. Huh? For me, S is equal to G. Okay. Okay. I'll try to not confuse notation. Okay. And then we did the following then. Okay. We went to what is called frozen formulation. Well, what are first class variables? This is the terminology of Dirac constraint theory. If you look in Henno's book or something like that, you will find this. They commute with all or have weakly zero Poisson brackets with all constraints. In general, these are difficult to find, but here, what are they? Okay, they are here. They are rather easy to find. One was this Ti. Okay, but Ti is the same as equal to Si, because Ti minus Si is a constraint. Okay, but actually there was nothing more. Okay, but with okay, T squared is equal to lambda squared, and the Poisson bracketed T's are given there. Okay, so if you quantize, so the and the polynomials thereon. I mean, once you write this, you can take all possible polynomials. Okay, okay. So here, and their polynomials, and in Ti. Okay, they will all have zero Poisson bracket. So last time we looked at what is called frozen formulation, frozen formalism. So here the constraints Hamilton, all of them are irrelevant. Okay, so what we do is just quantize first class variables okay, which we would call as observables. But here, since the T's are, so on quantization, what you have got is, so on quantization they go into operators T hat I, T hat J is I epsilon ij k, T hat k, with T hat dot T hat is lambda squared. So it's a Casimir. So you can see that this is an angular momentum algebra. So okay, can quantize only if okay, lambda squared is j into j plus 1 okay, for some j okay, belonging to 0, half, then you get. So for this choice of j, you get a particular quantity system with fixed angular momentum j. Okay, gives okay, states okay, gives a IRR of IRR j of SU2. That's it. Okay. But the funny thing here is, well, unusual thing is here, note, lambda is irrational. Because it's square root of this object. Okay. This is not what normally in the normal procedures, most calculations which come in field theory, the analog of this term, this lambda will be integral or half integral. But you can see that that need not be the case. It depends on how you quantize. Okay? In the frozen formulation, for these systems, it is definitely not true. Okay? Now I will do what I will call I will call Gupta-Bloiler. Method. This is another way. Okay, this is also okay highest rate representation. I mean, goes by various names. Okay, I think Fermi. Okay, as in Virasoro. Okay. In fact, we will see quickly that this system I am writing has a very close correspondence to Virasoro. You are getting, I will show you, a certain central extension of the Anglo-momentum algebra. Okay. Of course, well, Anglo-momentum algebra has no non-trivial central extension, but once you fix the operators, you cannot take it away. So we will see how it works. Okay. So let me do one thing. Okay. I want to define. Okay. To simplify the situation, okay, angular momentum operators let me call it some u, some other notation. Let me call it T prime I acting on S on the right. So I want to write Poisson bracket of T hat I G, or acting on G. I want to write operators which are going like G I sigma I over 2. The minus sign comes because it's acting from the wrong side. Okay, so to have the correct commutation relations, you need the minus sign. Left action, right action. This is the usual difference. So I want to define these operators. T hat, no, T prime I. Okay. So for that we notice the following. Okay, set G. Let's write. We know this following to be true. Sigma I G inverse. I want to. This is the usual. Some of you know that this is the usual map from SU2 into SO3. Okay. So R is defined by G, but plus and minus of G go to the same R. So this is a twofold. This is a the mapping, covering map from SU2 into SO3. Okay. Why did I do this? Well, then if let me write T prime I think there is a minus sign, minus, let me try, okay, Tj Rji of G simply linear combination of the T's. Okay, the Poisson bracket of T prime I with G is minus G will of course commute to this, so it is minus, so I sigma j over 2 G, okay, times Rji of G. which is equal to minus I over 2 sigma j r j I, which is g sigma I g inverse then g. Okay. So this is minus, just as I want, minus g I sigma I over 2. So this is the map which takes you from the left operators to the right operators. Okay. It is used quite extensively if any of you have studied Skrimion physics. Such soliton physics is or rotational models of nuclei, Bohr and Mottl or something. You will find this all over the place. So anyway, this is given. Okay. So let me see also what happens if I multiply SI spin operators times. So I want to know what happens if I look at this side, this object. This is the spin operator. This is equal to trace of, there is a lambda trace of, okay, sigma j over 2 g sigma 3 g inverse by definition. I am just using the definition of g sigma 3 g inverse as the spin up to lambda. Okay. So this is this object. I am multiplying this by r j I of g. So this is equal to lambda over 2 trace, okay, this object here. So it is g sigma I g inverse g sigma 3 g inverse So you see that there is a really significant simplification here, because you get a you simply get lambda times delta this I3. Yes. Okay. So if I replace constraints Pi by P prime I, which is Pi Rji of G, which is what I had Tj minus Sj okay. This is a great advantage. Simply the right angular momentum minus delta I lambda delta. Okay. So the constraints are okay. In this I can equally well write this as these are weakly 0 T prime 2 is weakly 0 and T prime 3 is not 0, is minus lambda. Yes. Why the constraints don't close? T prime 1, T prime 2 is just T prime 3, but that is not a constraint. So if I rewrite this as a constraint, okay, plus lambda minus lambda. Yes. So you find that there is a constraints are spoiled by a central term. Okay. This is the source of the this is the issue. How am I going to handle this? Okay. This is like L plus Ln in Beresford algebra. You may know Ln L minus n is not L3. Okay, Ln, you know this algebra. It's not L0, but this is whatever it is, C times whatever it is. I'm not C into C minus something divided by 12. Huh? Huh?
N into n square minus 1.
Yeah.
C by 12
C by 12 n into n minus
n square minus 1.
something like this, right? It is analog of this term here. Okay. But in a finite dimensional case, it is true that you can redefine these operators and get rid of it. Okay.
But when you are saying, writing it like lambda minus lambda, that you could have done anyway for any kind of constraint. This central, I didn't understand the statement when you are saying that it's the central charge term that you have written it like T3 prime plus lambda minus lambda.
This is 0 on the state. Suppose I impose them as constraints. The constraint algebra does not close. This is a constraint, this is a constraint, this is a constraint, but it is not closing as a algebra. Okay? So I cannot impose it on the quantum states, right? So these do not form a first class constraint. So only from here you see that only this one, okay, T prime, this constraint P prime 3, which is T prime 3 plus lambda, is a first class constraint. Okay, because this is first class because acting on T1 and T2, it commutes with all the constraints. Okay, commutes with itself, but these two are second class. Okay, so we can try eliminating them by Dirac brackets, but now comes the trick here. Okay? So
These are primary, secondary, tertiary one, or this T1, T2, T3?
there was only primary constraints in this problem. Okay, there was no secondary constraint, but already at the primary level we found 3 constraints. Remember, okay, because it's first order Lagrangian, so you get 3 constraints. Okay? Every momentum is a constraint. Okay. So only this is a first class constraint. So what do we do? Okay. But note, let me say, let me like this. Okay. Classically, two real constraints namely T1, say T prime 1, T prime 2 is same as one complex constraint. Which I will call T prime plus, this is T prime 1 plus I T prime 2. This is only a classical statement, and I have introduced a particular way of taking linear combinations. Okay. If you choose something else, okay, say 2 here, the method will not work. Okay. The reason in this is the following. Then, so what I will say is quantum mechanically, so we are changing the rules of quantization. Okay. So assume T prime plus and T prime 3 plus lambda are our quantum constraints. This is very similar to what Gupta and Fermi did, okay? Because he tried to impose the Fermi case, they imposed divergence. In the Gupta-Bloiler case, you impose this condition, okay, on the states. Right? Then you suddenly find that you cannot do this because the commutator of with this is not 0. Okay? So what do? You replace it by the annihilation part. Right? You change the rules of the game. Okay? But in complex, you introduce a polarization. That is, you split the modes of A into a positive frequency part and a negative frequency part. Okay? So you are introducing a complex structure. You are introducing I in the game. Okay? There was no I until now, but you are suddenly bringing an I. Okay? So if you do this, okay, then
what do you mean with quantum constraint?
I am going to impose this as conditions on the quantum states. So or to be used for quantization. That's what I mean. Classically, if you write like this, you can take real and imaginary parts. But if you apply an operator on a quantum state, you cannot take real and imaginary part of that quantum operator. Okay. Okay. So why do I do it? Okay. So let me call this P plus prime and P3 prime. Then P prime 3, P prime plus. This is going by the Poisson brackets. Okay. T prime 3 with 1, right? 3 with 1 is 2. Is P prime 2 minus I think. Let me get the signs right. I want to get back P prime. This is a raising operator. So I want to get J3 with J1 is I J2, right? Yeah. J3 with J1 is I P prime 2, J3 with, I am getting confused. J1 plus I J2, right? There is an I here. So it should be I, J3 with J2 is minus I P prime 1. So this is simply equal to P prime plus. They are close. Okay. So on quantization, so quantize, okay, imposing these conditions. Let me call them T hat plus and T hat 3 plus lambda. Okay. Now if we choose, okay, it's a convention, not exactly, but lambda to be negative. Okay, by if not, if it were positive, okay, okay, let G goes into G times I sigma 2. Okay, so you get G sigma 3 G dagger, this is anti-commutes, no? Would be minus lambda G, this is G prime. minus lambda G sigma 3 G dagger. Okay. So I can flip by just a simple redefinition. Say convention. If you don't want to do this, I would have to use T minus T hat minus here. You don't have a choice in this. Okay. So now I want to quantize. These are right operators. Okay. So okay, the best thing is okay, the unique okay, function of S, okay, where okay, these operators vanish, the constraints vanish. You can see why. Is okay, what? It is going to be d lambda m lambda of S of G is this one. Okay. So lambda belongs to 0, half, it's acting on the right. Okay. So the wave function is simply of the form. So this wave function is dj m j, where m is going from minus j to plus j. Why? It's like a raising operator, no? So if I raise lambda, there is nothing to raise, so it vanishes. Okay. It's a highest wave state. Okay. And this other one, I made lambda negative because then this thing will vanish. Okay. Your T hat 3 is equal to the value of this lambda, which I chose to be plus. So this is the highest wave state in the literal sense of the standard terminology. So you get what? You get a, we get okay, just an angular momentum J IRR for T for this operator is T hat I, right? T hat I act on the, this function of G, the T hat I act on the left, so they rotate the index M. That doesn't, constraint is acting on the right. Okay. So if constraint is on one side, the other one is on the other side. Okay. So they are mutually compatible, and we have chosen the highest wave state on the right. So this is what is called as the induced representation from a highest weight state. This is exactly what you do with the Veresud algebra. Okay. You take a highest weight state, or Kasputi, whatever. Then you induce it, at least you can imagine that it is being induced on the entire diffeomorphism group, okay, of the circle. The whole representation gives you a representation of the centrally extended circle group, but it is within quotes diffeomorphism invariant because in the space fixed frame acting on the right, the constraints vanish. So diffeomorphism generators vanish. It is exactly the same. Okay. So this is a baby version of what happens. See most of the features here. Okay. What is striking is here the spectrum of lambda. Okay. The spectrum, what the restriction on lambda is not equivalent to the frozen formulation. Okay. Is not that from what I call frozen formulation. Okay, the two methods are inequivalent.
Which one is the right way?
Sorry,
Which one is the correct?
there is no correct way, no, because correct way would be to start from quantum theory, right, and have it classical Lagrangian is. So it shows that quantization is not a unique idea. Okay. Classically, you are trying to massage it into a quantum theory, and you end up with different ways of doing it. That's it. There is nothing. Neither is inconsistent.
So there are two different quantum theories there,
They are different quantum theories.
but do they describe the same physical system? No.
I don't know what to say. Okay. In this case, yes. If you tune the lambdas, this you will get the same thing because
There is an overlap of lambdas between these two
yeah,
theories.
right. In this case,
So they are identical theories.
they are identical, but in general that is not true. There are cases where this is simply not true. Okay. For example, treatment of anomalies is very well known in the treatment of anomalies that you can regularize. For example, axial anomaly, you can regularize keeping the vector anomalies intact, which is what we often do, or the axial. You can also do the activity so that gamma 5 is good symmetry. Is a bad choice. Okay, axial group is good symmetry, which is, but you will get a theory which you don't want. Okay, so you don't do it. But if you insist, you can do it. So the passage to quantum theory is from a classical model is flawed with pitfalls. Okay, that is what it says. Okay. It's not. But what is interesting here?
There is this method of geometric quantization.
This is the same as geometric quantization is more elaborate, but is close to that. This
So if I did geometric quantization,
there it is situation is
which one would I get? Or is there a choice of polarizations that you were talking about?
there also they get stuck. Geometric quantization,
There's ambiguity, I agree. But
yeah. So far as I know, harmonic oscillator, they have to do an elaborate formulation to resolve the problem to get the answer that one wants. Okay.
downstate.
Even for the harmonic oscillator, but I don't remember the details. What is beautiful about that is there is a canonical map from the classical. How did it go? There is a canonical way of constructing an appropriate bundle structure on the classical phase space. Okay. Then the same problem comes, how to cut it in half. So they are actually starting from functions of Q and P, where every operator is realized nicely and so on. Then how to cut it in half. Okay. So there the trouble starts.
The issue of polarization.
Polarization.
What you call Qs and what you
Right. I am not remembering, but the person who used to know it quite well was Mukunda. Okay. He used to know it. I remember having read some notes by him on this. Okay. But I did not pursue it because it looked flawed. They themselves were saying it is flawed. So then it was slowly abandoned. But this way of doing, okay, is related to technical remarks. Before I go into something else. I should say whale bot. They do this. By the way, we know. Notice that this thing I am writing. Okay, note. Okay, as a preliminary thing. Okay, these are technical remarks. Fortuitously, I am giving it to you free. Okay, the situation is following. Okay, some identities. It is true that if I look at this one form, take this one form I lambda trace G inverse dg. you can see it's a small exercise, actually nice exercise, is I am not sure of my fact is this is nothing but d cos theta d phi. Volume form on the sphere. Okay. So, but this thing cannot be written. This A is not living in on the sphere. Okay. So, this A is living not on the sphere but somewhere else. Okay. It is lying on some bundle. The extra degree of freedom is here. Okay. But that extra degree of freedom, okay, disappears. So when you this in dA, it automatically goes away. So one can prove. This is a remark. Okay. Okay. This is an identity. Also, okay, we can write. We can discuss. Okay, Lagrangians. There is no magnetic field.
Well, dA is like volume form.
I'll tell. Okay, it's not a
Monopole in the center.
no. I'll come to the monopole. It is more complicated. Not more complicated. It's slightly different. Okay. You can also discuss Lagrangian for any Lie group. Okay. For any Lie group, which is something I trace K G inverse dg G dot. Okay. K is an element of the Lie algebra, Lie group G. Okay. And G is an G of psi is in G. I can write like this. Okay. Then what will happen is again dl d of this. Okay. Again if H is a stability group, sorry, maybe I am okay. That is K H inverse is K, H is in H. P of I trace K can prove, not very difficult. Okay, is a form. Okay, a 2 form on G over H. Okay. So all these things that I am somehow resolving a 2 form. These 2 forms are generally close but not exact, but I am resolving it by going to a larger thing. So what do they, now I say it and then go on. Borel Weilbot say, Weilbot I should prove, well, is actually the following statement is true. Any orbit in the Lie algebra is even dimensional so it is any orbit in the Lie algebra, okay, is even dimensional. That means this object GKG inverse is even. Statement 1. This result is due to Kostas and Kirillov, okay, and also Suryo. You understand? If you take an orbit, it's not difficult again to prove. Okay, this is Kostas and Kirillov. Suryo, I can't pronounce. I am sure that some of you, what I am saying may not make sense. Okay, but if you take this object here, for example, on a sphere, G sigma 3 G inverse is a sphere, it's a two-dimensional object. Okay. If you take SU3 and we put hypercharge here, you know what happens? What do you get? You get CP2, okay, which is an even dimensional real manifold. Okay, and so on. If you take some other operator for SU3, you will get some six-dimensional manifold. Okay, but always even. Okay. Statement is 1. They are all. I am just trying to tell you symplectic, okay, with a closed 2 form. Omega, in fact, the one above. That is, omega is d of, I can write this as d of I trace k G inverse dg. This until now there is no problem. Okay. Then comes the following. Okay. If omega 2 form, okay, belongs to is integral cohomology, that is, what does it mean? The integral of omega on any 2 sphere is belonging to Z in a 2 cycle. Here is a technical notation. You are looking at second cohomology of J over H with coefficients and integers, which is simple. Another way of saying that if I integrate omega on a 2 sphere, I get an integer. Okay. There exists, here I have to use this, a UN bundle. Okay. Call it bundle space is E. Okay. The UN bundle, okay, over G over H, and this is what you would call connection, one form A, okay, such that dA, okay, dA actually is a 2 form here, okay, it projects down, let me write it loosely as my omega. What this means is if I take dA, it is U1 invariant projects down. This is not exactly correct, I have to. So we have a connection and a bundle with a connection. And you can, okay, then the Borel value, so this is the integrality in their way is necessary to get this bundle at all. Okay. Once you have that, let me say this simply. Okay. There is also then there is a canonical way of finding representation, irreducible representation of G, okay, on sections of this bundle. I will deviate too much. I already said too much, I think. So you need some polarization, but it is given already by the Lie algebra. That is, once you give k, there is a way to split the Lie algebra into positive roots and negative roots. Okay, that gives you a polarization. Okay. But the whole thing can be carried through. There is a paper. So this is a connection. Why in their thing the lambda? So what did I do? I got the Borel-Weisbart result here by starting from a Lagrangian and applying constraint theory. Okay, so let us see. So we got Borel-Weisbart, okay, from a Lagrangian. That's what I have done. Okay. When we were much more innocent of all this, I wrote a paper with, I think, yeah, Borchardt and Stern. Then much later, I wrote a paper with George Mirzi, Peter Preschneider. This is an older paper in, I think, Physical Review. This is in JMP. This paper, once we got the spin system worked out, we thought, why don't we write I trace k G inverse dg, G dot, and quantize. Then we got naturally all kinds of problems arise in higher groups. Okay. And we tried to resolve it. I think we did resolve it. So that is a straightforward approach to quantizing particles, to finding all irreducible representations of a compact Lie group. Okay. But in that paper, what is missing is this polarization part. Okay. We did not know about it. How to introduces i's, okay, in the Lie algebra. We did not know that you can apply, even we did not even know we can apply Gupta-Bloiler type arguments, but by the time we were much older, so we knew it. So it is discussed here. But this is more about writing Dirac operators, stuff, spin structures on G over H, and things of this kind. But at some point, we discuss why all these G over H's are Kähler, and we find a Kähler potential, and some of you would be interested in this. Okay? And there are some very strange things that happen, okay, which we discussed here. What is the strange thing? You may know that not all manifolds admit spinors, okay, if you know it. Okay? One example is this CP2. CP2 you cannot write Dirac spinors. But it has a spin C structure, right? Which means you have to introduce half a monopole. The monopole is not quantized properly, nor is the spin, but still you can write spinors which carry this Fermi charge, Fermi magnetic charge. But there are manifolds which will not even admit spin C. Okay. So this is U1 or spin E1. What you are doing is to twist something with, and there are things. The example is SU3 over SO3. It's a 5-dimensional manifold which does not admit even spin C. So you have to go into spin SO3. That is, you have to twist with the higher rank. The internal, suddenly you find that to define spinors you have to introduce internal degrees of freedom. Okay. So we've discovered this, but it is known in the maths literature, and for a long, and it discusses how this happens in our language. But I have been wondering very long whether it has any application in string theory, because if you take a manifold with this thing and try to put spinors, you cannot do it unless you bring a minimum of several, is a 5-dimensional manifold, okay, enough of them so that you can they all merge to form a spin, something capable of support. So the extra degrees of freedom will come from the d branes which are coalescing. Okay. So I was wondering whether it has any application to that context, but since I am not a string theorist, we never pursued it. So anyway, this was an I am conscious that this was a major sideways activity. Okay. So I want to look at magnetic monopoles, then go directly into Chern-Simons. Okay. This aside was maybe unwise, I don't know, but I think the time is over, so you can ask me questions or do whatever. Okay. Yeah, oh yeah, I should say this is quite interesting. It was already shown, let me say, if you take Casbody, okay, for the Casbody, again you can construct the constant Kirillov activity. Do you know what is a co-adjoint group? Okay, okay. Forget about, think of it as a Lie algebra. If you have a Lie group, Lie algebra, see, it's not, see, the Virasoro and so on are not so what you see, you cannot write a Virasoro algebra and take a trace with an element. There is a problem there, okay, or Casbody, you will do something. So if you give me a group, there is a Lie algebra, okay, so a group G, so Lie algebra is G, so it is spanned by some there are some vectors K in this, okay, right. Then it is a vector space at each point, so these are vectors, these are Lie algebra at the origin. Then there is a dual space, there is K has a dual space. So this is a complex number. Right, is a vector space we have to do, okay, upstairs. Then the group acts here, by definition is the same as some new action new dual. By definition, this is a definition. So this is called the co-adjoint action. You can work it out. Okay. If this thing can be written as a trace, then you just use a trace as I did. But many times you can't write it as a trace. You have to write like this.
So that will give you a restriction on what. So
no, what I want to say is the theorem of Kostan and Kirillov is that this co-adjoint orbit, or you take an orbit, you pick one element of the co-adjoint space and act with the group like this. Okay, you get some space. Kostan Kirillov tell you is always even dimensional simplicity. Okay, is an amazing fact. For Lie groups, semi-simple Lie groups which admitted this trace, there is you can write it in terms of trace and K check, but generally it's true. Okay, so already in I think in Presley-Siegel, they looked at Casbody from this language, and I think it is implicitly there, but later I think Vincent Rogers, who was my student, okay, and another one whom I am not remembering, did it for Casbody like along these lines, and you know what they got? They got the Vezuvino-Witten model in 2 dimensions. Okay, this Vezuvino-Witten action completely. What is it? G inverse G dot plus the cubic term. So that action is, why are you getting such simple answers? Because you are just looking at a representation of the Casbody algebra, which Witten says, okay, in his paper, and no wonder, because you are generalizing Borel-Weilbot to infinite dimensions in the Casbody case. That is all you are doing. Okay. So it is not, and Presley-Siegel already somewhat discussed it. Okay. So this Vincent, somebody else, I told them to look at it, and they did, and they got this. Quite amazing. Then our friend Raji picked it up, and he applied it to Virasoro with Mark Bowick. Okay, you get an action. He thought it will be the action of strings. Okay, completely diffeomorphism will vary and so on. He wrote it. Okay, and they looked at several features. Something did not work. Okay, then Ed was very excited, I think. So he started applying this to all kinds of groups, including SL2R, infinite dimensional groups, infinite dimensional non-compact groups. Okay, and then he very quick. So this activity is every one of the extra terms which are coming as topological terms that I know in quantum theory, which give you anomalies in chiral models, all kind. They are all coming from an appropriate group. Could be a loop group acting on the coadjoint orbit, and they are coming from an appropriate 2 form. So this is some of the core of the anomalies in quantum field theory. One way of writing it, because you are adding terms in the Lagrangian which changes the simplicity form, and that changes the physics. So the last half an hour I have been giving you lots of information, okay, but I did not do any calculation. Okay, it will take me too far afield, and time is limited. So next time I will do, honestly, I will do monopause. Then I will do Chern-Simons, and I will try to tailor the Chern-Simons in such a way that you will see why it is important to know it in the context of, say, treatment of constraints in gravity. What is how the ADM mass and ADM generators arise in that context, or how electric charge is defined in QED, you see can be seen already here in the 2-dimensional Chern-Simons, 2+1. So I will do that.